Welcome back. We're now starting module number 4, which is the shortest of the 5 modules, just a few sections in chapter 21. Remember, the topics in this course were chosen for at least one of two different reasons. One is that they are relatively new in terms of the history of mathematics, and therefore still of interest in mathematical research. The other is that they would be of practical importance, at least to somebody in the world. In other words, somebody in their daily life is using this particular kind of mathematics right now. The topic of Module 4 is savings and investment. It's certainly not a new topic. People have been saving, borrowing, investing money for thousands of years. It is a topic of very practical importance, to you even, I claim. You are going to, at some point in your life, perhaps buy a house, send your children to college, buy a car, retire, and hope to live off of your savings, and other types of investments perhaps as well. And increasingly, you're being asked by society to take charge of your own financial planning. In your grandparents' day, maybe your grandfather worked and eventually was eligible for a pension, and his company just paid him money in retirement. And there still is Social Security, but that won't pay all that you need for retirement. You're going to be the one who's responsible for saving up enough money so that when you retire, you're able to live comfortably, or to send your kids to college, or to buy your house and make the payments on it, and so on. We're not going to look at investing and borrowing in all that much detail. That would be a topic for a business and finance class. We are going to look at the mathematics that goes into the behind the principles of saving and investing, and in particular looking at simple and compound interest. First, let's just take a look at a table here. This is taken from a website of a credit union, my credit union in fact, where Indiana Wesleyan employees and Marian School employees can open accounts. These are rates for certificates of deposit. So you can invest money in this particular credit union for various lengths of time, and the credit union will pay you interest at various rates for those various investment periods. Notice that in general, the longer you're willing to invest your money, the higher of an interest rate the credit union will pay you on your investment. And one of the places that I want to get today in this lecture is a discussion of what annual percentage yield means. Notice that the figures for annual percentage yield are just very slightly larger than the so-called dividend rate, and this has to do with the fact that the money is being compounded. So the very last thing I want to do in this lecture is discuss annual percentage yield. Over here is just some information about minimum investments and so on, just policies of the particular credit union. Before we get to annual percentage yield, let's look at some easier kinds of questions dealing with compound interest. So suppose you have a bank account that pays you 4% annual interest compounded monthly. The types of questions that you might want to answer for investment or borrowing purposes: if you put away $1,000 now in this account, how much will you have in the account after 10 years? Or kind of a converse question: if you know you need to have $1,000 in the 10 years to buy something, then what do you have to put away as an investment now? Or just a multiple choice, how's your intuition type of question. Which would you rather have? Somebody give you $1,000 now, $1,100 in 5 years, or $1,300 in 10 years from now? Question number 4 is perhaps the most realistic of the 4 questions. We'll postpone that until the next lecture. But let's look at the mathematics behind questions 1, 2, and 3. Let's talk about interest, and I want to contrast simple and compound interest. If you're not familiar with the terms, simple interest just pays you on the principal, on the amount you invested, whereas compound interest pays you both on the principal and on the previous interest. So in compound interest, you earn interest on the interest. In simple interest, you don't do that. Most investment situations actually involve compound interest. A bank account, for example, compounds your interest. One type of investment where interest is not compounded is something called a bond. And this is how companies or city governments, state governments raise money. They have a large project they want to do, so they need a lot of money now. And they raise the money by selling bonds, and then consumers like us can buy those bonds. A bond is a fixed term and fixed rate investment that pays the buyer simple interest on the principal throughout the term, then returns the principal at the bond's maturity date, or at the end of the investment period. Question: if you buy a 10-year, $1,000 bond today, earning simple 4% annual interest paid annually, how much money would you have in 10 years? So the way the bond works is I give the city government some money now, and over the next 10 years, each year I get an interest check. The city government pays me an interest check each year for the next 10 years. At the end of the 10 years, they give me my $1,000 back. Let's look at how you might mathematically answer this question. First of all, we're going to start out with $1,000, and then let's talk about how much we have in 1 year, 2 years, 3 years from now, and then try to come up with a general formula. After 1 year, what do you have? Well, though the government hasn't paid you your $1,000 back, you still have it. It's yours. They're using it, but it's still yours. And then you've earned 1 year's worth of interest on that $1,000. So you're investing $1,000 at 4% interest, so times 0.04. So this is the principal. This is the amount of interest that the government is going to pay you at the end of the first year. And rather than work out what this number is, let me mathematically manipulate it. Both terms, notice, have a factor of 1,000. Let's pull that out. And then when you pull 1,000 out of 1,000, you leave a 1. And when you pull 1,000 out of the second term, you leave the factor 0.04. I'll leave that for purposes of pattern recognition as we get some other computations going. How about after 2 years? Well, you still have your original $1,000 put away. Then you have interest from the first year. It's actually already been paid to you. And then you also get interest on the second year. So what's going on here? This is principal. First year interest and second year interest. And let me rewrite this as well. I can pull 1,000 out of each term again, and that leaves 1 plus, and then there's going to be a 0.04 here, plus another 0.04 coming from the third term. So there are 2 copies of a 0.04, and let me write that then as 0.04 times 2. So the 1,000 came out. The first term generated the 1, and then each of the second and third terms generated a term of 0.04. There are 2 of them. And now maybe you see the pattern. After 1 year, this is what the expression looks like. After 2 years, this is what the expression looks like. So how about after 3 years? Well, if I follow the pattern, 1,000 times quantity 1 plus 0.04 times 3, because there are 3 years to earn interest, so 3 copies of the 1,000 times the 0.04. And now we have a pattern that's recognizable. After t years. So I'm switching from computing a number now to generating a formula. After t years, how much money should I have? 1,000 times 1 plus 0.04 times t. And now t can be 1 year, or 3 years, or 10 years, or 50 years. All I have to do then is plug the number of years in for t and crank out the number, which tells me how much I have earned. So to answer the question, we were asked to put money away for 10 years, and so 1,000 times 1 plus 0.04 times 10, plugging in t equals 10, and this is a number that you can compute on your calculator. It's $1,400. That's what you would make by buying this bond as a 10-year investment with simple interest. Okay, let's do a question that comes from a bank savings account or bank certificate of deposit. $1,000 is deposited in a bank CD, earning 4% interest again, but this time the interest is compounded annually, compounded one time per year. Now how much will be in the account after 10 years? Again, I'm going to go through some generating the pattern and then try and guess a formula. We start out with $1,000 as before. After 1 year, we have our $1,000 and we've earned a year's worth of interest on it. So it looks like this. Just as we did before, I'm going to factor the $1,000 out. So you get 1 plus 0.04, and I'm going to rewrite this as, well, 1 plus 0.04 is 1.04, like this. Alright, after the second year, what's going on? Well, I have this amount that I had after the first year. So going from the first year to the second year, do a computation for the second year. Take the amount that I had at the beginning of the second year, or at the end of the first year, for the same thing, and now that same amount has earned interest for 1 year. So I can think about it being like this. Here's my principal, dealing just with the second year, and then here's that amount that I have at the beginning of the second year, and it's earned interest for a year at 4%. So this is the amount of the whole second term is the amount of interest that I earned during the second year. Let's work on this mathematically. I can actually factor a 1,000 and a 1.04 out of both terms. I'll do that. And then left over, well, out of the first term I've pulled out both of the two factors here, so that just leaves a 1. Then here's the plus sign, and now I've pulled out both terms in the square brackets, and that leaves the 0.04, this factor at that was at the very end. Let's simplify this a little more. 1,000 times, okay, here's one factor of 1.04. But notice in the second set of parentheses, there's another factor of 1.04. So we'll write that as 1.04 squared. Now can you see a pattern? After 1 year, 1,000 times 1.04 to the first power. After the second year, 1,000 times 1.04 to the second power. After 3 years, 1,000 times 1.04 cubed, or to the third power. And as a formula, after t years, 1,000 times 1.04 to the t. And now again, t can be 3, it can be 7, it can be 15, however many years I'm investing in this CD. Plug that value in for t and crank out the number. So this problem again asks us to invest for 10 years. So amount is 1,000 times 1.04 to the 10. And This can be computed on a calculator. By the way, just as a sanity check or an intuition check, for simple interest we got $1,400. At the same interest rate with compound interest for 10 years, are we going to get more than $1,400 or less than $1,400, do you think? If you think about it, we should get more than $1,400 because this is compound interest. We're earning interest on the interest as the investment period goes along. So this should be more than $1,400, and indeed it is. It turns out to be 1480.24 to the nearest penny. In these types of calculations, usually I'm going to round the answer to the nearest penny. Now, this is something that you will have to compute on your calculator, and I don't know what kind of calculator you have, and I can't possibly demonstrate every possible brand of calculator because I'm sure you have different ones. But make sure that you can do this, and if you have questions about it and want to contact me, maybe I can look up your particular brand of calculator and help with keystrokes. Now let's look at the theory behind this, or actually formulas behind this. In general, here's the terminology that we're going to use, the notation that we're going to use, and it's the same as the textbook uses. P is the principal. It's the amount that we originally invested. R is the interest rate, and as the problems get more involved and involve different kinds of interest, this is going to be what's called the nominal or simple interest rate. T is the number of years of the investment. A is the amount at the end of the investment period. And now simple interest, the formula looks as follows. A equals P times 1 plus RT. Remember the formula that we developed for simple interest here? A equals, the $1,000 was the P, the principal we invested, times the quantity, 1 plus, this was R, the interest rate, it was 4%. And by the way, you always convert interest rates to decimal fractions, 4% is 0.04. And then this is the T, the time period of the investment. For compound interest, if interest is compounded once per year, it's a formula that looks like this. A equals P times 1 plus R to the T. That's the formula that we developed for compound interest. It's right here. 1,000 is the P, the principal, and then here is the 1 plus R, the 1 plus the 0.04, and then here's to the T power. Now let's push this formula a little bit farther. Sometimes interest is not compounded once per year, but more often. In fact, most banks compound interest monthly, 12 times per year. Or maybe you could find a situation where interest is compounded daily, 365 times per year. Let's use the book's notation. We'll write the letter I for the R divided by M. This is the annual interest rate divided by how many times per year the interest is compounded. So if you think about it, if you have a 6% interest rate, for example, and interest is compounded twice per year, that's like having a 3% interest rate but for a half a year, and then 3% interest rate for the second half of the year. And that's sort of like having 6% interest for the entire year. Then N we'll use for the number of compounding periods, and that's M times T. So if interest is compounded, say, 3 times per year for 5 years, then 15 times over the investment period the interest will be compounded. And then the change in this formula that's going to be made is A equals P times quantity 1 plus. Instead of using R, we'll use R divided by M. The interest gets divided over the number of times per year. By the way, here's a typo. This should be an M times per year. And the T gets replaced by MT, because if it's compounding 3 times per year, then 3 times the number of years is the number of compounding periods. Then in this simpler notation with the I and the n, p times quantity 1 plus I to the nth power. Now let's go back and answer those questions that we were asking, I was asking at the beginning. Suppose you have an account paying 4% annual interest compounded monthly. Question number 1, if you invest $1,000 now, how much will you have in the account after 10 years? So first of all, interest is compounded. So first thing to do in questions like this is to identify whether you're talking about simple or compound interest. In this case, we're obviously talking about compound interest, and so I'll use the compound interest formula. And by the way, you don't need to memorize these formulas. On the next test, you'll get a formula sheet, or the formulas will be given in the individual problems, perhaps. So you'll be able to use them and know what the variables in them mean, but you don't have to memorize them. So the compound interest formula is this. And now, what's what? How much will you have in the account after 10 years? That's the answer to the question, and that is the A. So we're supposed to find A, the final amount in this particular question. P. P is the starting principal. It's how much you initially invested. For this problem, it's $1,000 times the quantity, 1 plus a fraction. R is the nominal interest rate. For this problem, it's 4%. M is the number of times per year that interest is compounded. Interest is compounded monthly in this problem. That's 12 times per year. And the exponent is the product of M. That's the number of times per year interest is compounded. That's the 12 again. Times T. That's the number of years that the investment is made. And in this case, it's 10. So this is an expression to plug in on the calculator. All right, suggestion for calculator problems. Remember, there's an order of operations that says do things in parentheses first, and then exponents get done before multiplication, which in turn gets done before addition. Here, there's actually a grouping around the 12 times the 10. The 12 must be multiplied by the 10 first before you raise it, before you raise this expression to the exponent. As you're entering in your calculator, if you don't use parentheses around the 12 times the 10, it's actually going to assume that you mean raise this expression to the 12th power and then multiply that by 10, whereas you really want to be multiplying the 12 times 10 and then raising to the power. So this is how you could directly enter it on your calculator then if you had a graphing calculator. 1000 parenthesis 1 plus 0.04 divided by 12 in parenthesis, and then to the, so on a graphing calculator at least, that's the caret symbol. On a regular scientific calculator, use your Y to the X button, and you'll have to enter things in the proper order. And then parentheses around the 12 times 10 and close parentheses. Or you could just enter, you could do the multiplication to get 120 in your head and enter that. To check yourself, to make sure that you can get on your own calculator $1,490.83. Comment. Notice that that's a little more than the $1,080 when interest was compounded 1 time per year. So in general, the oftener the interest is compounded, here compounded 12 times per year instead of just 1 time per year, the oftener the interest is compounded, the more the principal will grow to. Second question. How much money do you have to invest right now to have $1,000 in your account 10 years from now? That's actually called the present value of $10,000. It's compound interest again, so here's our same formula. And now, what do we know and what do we want to know? We want to know what lump sum you would need to invest now. That's the starting investment. That's actually the P. You want to know the principal that you need to invest in order to have $1,000 in the account after 10 years. This is the final amount. This is the amount that you have after the investment period. So the A in this problem is the $1,000. P is what you want to know, and then 1 plus, and the R is 0.04, the M is 12 again, and the T is 10. Okay, so we want to know P. I can mathematically solve for P by dividing both sides by this big expression here. I'm dividing both sides by the expression that I circled in red, and then I'm actually going to write the P on the left-hand side instead of the right, because that's how we usually write a formula. Wouldn't have to, but typically done. So now it looks like this. And then here is what you can enter into your calculator. Again, there are some issues with the calculator. You want to make sure this entire denominator gets evaluated, that the exponentiation gets done before you do the division. So on your calculator, you probably actually want to use another set of parentheses around this, and as we discussed before, a set of parentheses around here. So this is actually then directly what you could enter on a graphing calculator. Make sure that you can get $670.77. Sanity check. Notice that it needs to be less than $1,000. You're going to invest something now and you hope to have it grow to $1,000. Surely you shouldn't have to start with $1,000 or anything greater than that. You should be able to start with something less than $1,000, have it grow up to the $1,000. Third question, what would you prefer? Somebody gives you $1,000 now, $1,100 in 5 years, or $1,300 in 10 years. Well, this is money now. This is money 5 years in the future. This is money 10 years in the future. Let's actually pull these amounts back to their present value. We'll compute the present value of this, this, and this, and see which one is the biggest. So I'll call those A, B, and C. A, of course, is $1,000. For B, I need to do a present value computation. $1,100 is the final amount. What present value, starting principal, does that correspond to when you're talking about 4% interest compounded 12 times per year for 5 years? So this is the same type of computation as we just did. Solve for P and get $900.90. And for the third situation, the final amount is $1,300. You want to know the present value is investing at 4%, 12 years, 12 times per year rather, for 10 years. Solve for P and get $872. And so, which is best? Actually, in this case, the $1,000 is best for you. It gives you the most money, has the highest present value. Finally, let's get back to this annual percentage yield that I mentioned. That came from a certificate of deposit chart. You could also see this on loans. There's a rate and then an annual effective rate. I'll read the question. The annual percentage yield, also called the effective annual rate for a given interest rate with compounding, is, so its definition is, it's the simple interest rate that would yield the same amount of money over 1 year. And simple interest does not have compounding. So what's the APY, annual percentage yield, of a CD that pays 4% annual interest compounded monthly? All right, let's just pick a value to invest in a couple of situations, under the compound interest and under simple interest, and we'll compare those. I can pick any amount that I want, so the simplest thing I can think of is to pick $1. So first question, how much will $1 grow to in 1 year with this compound interest? I have 4% compounded monthly. All right, I use my compound interest formula. And I want to know how much it will grow to. In other words, find A. I'm investing $1. P is this dollar. 1 plus R is 4% interest. M is 12 compounding periods per year. And I'm investing this for 1 year, so T equals 1. Plug this into a calculator, it's 1.0407, and here I'm going to make an exception. I usually have been rounding things to the nearest penny, but here, to get more accuracy for the problem, I'm actually going to take it out to 4 decimal places or so. Second question then, what simple interest rate would grow $1 to this same amount in 1 year? So you can think about two banks sitting side by side. One of them pays you compound interest, one of them pays you simple interest. The one that pays you compound interest will grow your dollar to 1.0407. The one beside it pays simple interest. What interest rate would they have to pay so you could still end up with the 1.0407? Well, this is a simple interest problem, and so I'll go back to my simple interest formula that looked like this. And how much do I want to end up with? Same thing as I made with the compound interest. A is the 1.0407. How much am I investing? Still $1. What's the interest rate? That's what I'm trying to find, R. And what's the investment period? 1 year. Solve for R. This is an equation with one variable. In fact, it's really easy, because here's the expression in the parentheses times 1, so this 1 just goes away. And then I have 1 plus R on the right, and 1.0407 on the left. I subtract 1 from both sides, and I'll write R on the left, and I get 0.0407, or 4.07%. This is the annual percentage yield in this situation. Notice that's a little bit more than 4%. Because we're compounding, the 4% actually acts like 4.07% would under simple interest. So 4% compound interest is better than 4% simple interest. In fact, 4% compound interest corresponds to 4.07% simple interest, and that's what annual percentage yield is trying to tell you. That answers that question. One more thing to point out is that if I were to take this equality, set the compound amount to the simple amount, and solve, it would look like this. If I put the simple interest, say, on the left, the R that I was trying to solve for is actually the annual percentage yield. So this is what simple interest will do for you, and I want that to grow to the same thing as it would under compound interest. Here's our compound interest formula over 1 year. And so as a formula, the question is, okay, what is APY? What's a formula for APY? This is compound, setting simple interest equal to compound interest and solving for the annual percentage yield. The p's cancel on each side, and so I get 1 plus APY equals 1 plus R over M, that quantity to the M, and then if I solve for APY, I get 1 plus R over M to the M minus 1. And here's the formula for annual percentage yield that is in the book. And you don't need to memorize it. In fact, I probably wouldn't even have to give it to you. If you understand the meaning behind this computation, you wouldn't even need the individual formula. But I'll give it to you. And that finishes the topic for the day. We wanted to talk about simple and compound interest, and finished with the relationship between the two, which is annual percentage yield. Thank you.